squash, a simple plant that produces fruit and is, well, I won't say delicious, but you put it in garlic and butter and it's just fine. This squash plant is having several flowers growing right now. We can see a female flower right here. We got the flower head, and then we have this large ovary down here. Over here, we've got a male flower, the flower head, and there's no ovary. So it will produce just about every day a female flower or a male flower. And the bees and I will pollinate the female flowers using pollen from the male flowers. About 7 days later, we'll get a squash fruit, which will be just, well, edible. So we can count the number of squash fruit that we're going to get by knowing the number of female flowers we see. It is a directly proportional linear relationship between the two. The number of female squash flowers is the x-axis, and the number of squash fruit is going to be on the y-axis in pretty much a 1-to-1. It's also directly proportional to the number of sunny days we get. After a nice day like today, there should be one flower opening per squash plant in my garden. So I can use that linear function to predict how many squash I'm going to be eating in about a week. This linear relationship between two things can be measured using the statistical test known as linear regression. And how well two things relate is known as the coefficient, Pearson's coefficient. So if I wanted to know how well the number of flowers will predict the number of squash, I will use something like Pearson's coefficient. We also do have some other plants here. We have some butternut squash that I'm just trying to grow. And I have to be honest, it's my first year doing butternut squash, and I really don't know what I'm doing. They're turning the wrong color. So, yeah, ask me about that and how that ended up sometime, because right during I'm filming is the middle of the summer, but hopefully when you're watching, it's squash harvesting season. Linear regression and statistics review. That's what we're up to in this lecture. We are going to go through the simple ideas of linear regression, cover the two terms that are somewhat confusing, the r and the r squared. You may have already figured out the relation between those two. And this whole lecture is really about correlation. Remember, correlation does not imply causation. I want you to be able to compare r and r squared, and to, at the end of this, take some time to review statistical tests. So, linear regression is about data relations. How are two different facets, different x and y, how are those going to be related? So each data point has to have an x value and a y value. Here we have a graph showing that there is a certain score where someone scored an SAT of 800, 600, or 300 in math, and what the college GPA is. You may immediately think, there's definitely a relationship between those. It must be the SAT score in math is a good predictor of the college GPA score. The second thought might be, but look how much variability there is between those two. So while the line seems to imply a direct correlation, a direct relationship, one may begin to question whether that relationship is actually reliable. Now do remember that it's necessary that each data point has to be independent of one another. If they're not independent of one another, then the very things that tie them together are going to complicate the ability of the x value to explain what's going on in the y value. Also remember that this is a non-parametric test, so we are sampling from something that does not necessarily have a normal distribution. Now the SAT score and college GPA scores may have a normal distribution, but as we see right here, there's some relation, but is it a good relation? Well, is it a good relation? There is a way of telling that we will get to a little later. First off though, do remember, correlation is not causation. I used to believe correlation was causation, but then I took a statistics course. Around the same time, I learned that correlation is not causation. I don't know if the course helped or not, but it seems to be correlated. So correlation is just the relationship between two variables, and there can be a reason. Causation can be a reason. As the squash example showed, the sunny days cause there to be new squash. It's photosynthesis. Without a sunny day, there will not be squash. Another thing that I dealt with since being in the garden, I actually took a little extra time out there, was to snip away dead squash. Dead squash happen when there are a lot of rainy days and slugs are going to be eating them. So the number of squash I get is directly correlated to the number of sunny days and negatively correlated to the number of rainy days. And we do know that there is a causative factor there. Causation can be a rationale, but it can be that there are additional causes. Consider that when people eat ice cream, they also tend to be more likely to have sunburns. So it seems that ice cream must cause sunburns. So let's see, if ice cream and sunburns travel together, if I avoid ice cream, then I won't get a sunburn. So I'm going to be a strictly Frogurt kind of guy. And that'll mean I can play out in the hot, hot sun without getting a sunburn. Well, no, it's the hot, hot sun gives you a desire for ice cream or Frogurt, and also can cause a sunburn. So their correlation is between ice cream and sunburn is false. Now this can be easily found by just doing experimentation. We'll have one group that gets no ice cream, and another group that gets tons of ice cream. We'll see that they have equal sunburn rates. Well, it looks like that is not a causative factor. And you see there, by manipulating the x variable and using an additional statistical test, say a t-test, we could actually rule it out as a causative factor. There are different types of correlations. As I've kind of already mentioned, the linear relation. A linear relationship can be positive or it can be negative. Take, for example, the positive relationship between the number of sunny days and the number of squash I'm eating, and the negative relationship between the number of rainy days and the number of squash I'm eating. Because the positive has a causative factor of more sunlight, more photosynthesis, more squash. The negative has the relationship of more rainy days, more slugs, more dead squash. So there's a positive or a negative relationship. And these can have various values. If the line is just straight across the middle, it can actually mean there's just simply no relationship. There's also the quadratic relationship. I mentioned in an earlier lecture about carrots. How if I put carrots all the way down my garden, I may actually get a certain spot in my garden where the carrots grow best. And that would be because they don't get too much sun and dry out too fast, and they also don't get too little sun and grow too slow. That would be a quadratic relationship where there is a positive relationship and then a negative relationship, and there's a certain peak. Now, I actually do believe that through some experimentation, where I'm planting the carrots this year happens to be where I would find that peak. Last year, I put them where the potatoes were, and they're pretty similar demands. There are other types of relationships. So just kind of scroll down here in the bottom, other, and cover it very briefly, that there can be exponential, there can be logistic, there can be all different types of correlations, each of which can be explained by a certain type of function. Now we can explain the type here, but let's look at the strength of that function. So the correlation strength. When you think correlation, think relation, two things are related, and co-related. These two things are co-related. They're both working together in a certain fashion. So the strength of the relationship between the two variables can actually be measured pretty well by something called Pearson's coefficient. And that is simply Pearson's R, is equal to sigma with a range I for x sub I minus x bar times y sub I minus y bar divided by the square root of the sum from I of x sub I minus x bar squared times the square root, square root of the sum sub I of x sub I minus, y, am I doing this wrong? Y sub I minus y bar squared. What's all this then? Well, simple. It is actually simple. Every value, every data point has an x value and a y value. X bar is the average x. Y bar is the average y. So on a graph, we have a point x bar, y bar. A data point down here has a difference in x and a difference in y. This is y minus y bar. This is x minus x bar here. So that's the difference right there. So for each one of those data points that we may plot on this, they have a difference from the mean. And the idea here is the number of differences from the mean divided by the square root of the sum of the differences is actually going to be telling us how well they're related. So what direction they're going to be related in and the strength of the relationship. A Pearson's coefficient equal to 1 is strongly correlated positively. A Pearson's coefficient equal to -1 is, well, perfectly, I guess for one, perfectly correlated, but negatively. Anything between -1 and +1 is something less than a negative perfect relationship and a positive perfect relationship. A Pearson's coefficient of 0 is no relationship. If all of them just kind of cancel out each other, then it's just no relationship. And that's Pearson's coefficient, the strength of the relation between two variables. Want something easier? Me too. So let's discuss R squared. R squared is when you take Pearson's R and you multiply by itself. Okay? It's useful though. It's useful because what R squared does is it tells us how well the line that we may make for a line and for data points, how well does the line explain the variation in the data? So if all the data points are on the line, it's going to be a very good R squared. It's also going to be a very good R. An R of 1 equals an R squared of 1. An R of 0.5 equals an R squared of 0.25, because 0.5 squared is 0.25. Harken back to the days of Hardy-Weinberg. So R squared there is how well the line is explaining the data. This is a value we automatically get from Microsoft Excel. And now we know what it means. So even if we say we have an R squared of, say, 0.81, okay, I guess it's not that good because 19% of the variability is not explained by the line. Well, yeah, but it does mean that 90%, that these two things are correlated with a Pearson's R of 0.9, and that's good. For ecology, we often end up with pretty low values for R and R squared because we have a lot of variability that is introduced into the system. So harken back to the squash. Yes, if there is a sunny day, that's good for the squash, but is it a sunny day that is going to be a hot sunny day or a sunny day that is going to be a cool sunny day? You can probably guess that a hot sunny day is better for squash than a cool sunny day. So it's not just the amount of sunlight, it's the amount of temperature. And were the plants well watered beforehand or were they poorly watered? Is it a dry day or a humid day? And all these other variables are each going to introduce variability such that what we would believe of one flower, one squash after 7 days, perfect, is actually not that perfect. It's going to be one flower, wait 5 to 10 days for delivery. So linear regression is another test that can be used here. So we can get the r, we can get the r squared. It tells us something about the line and the data. But a linear regression, true linear regression, is an ANOVA test of the co-relationship between these two variables. And that's done using more complex statistical programs such as R, rather than using the statistical programs in Microsoft Excel. A linear regression is going to report a p-value as well on how well line explains a relationship. So even with a Pearson's coefficient of 0.5, we may still get a very good relationship that is still significant with a p-value less than 0.05. So it could be that the line actually explains the relationship pretty well. And with this, you want to report the R, which is telling you the strength of the relationship. And you want to report the F value, which is from the ANOVA. And you want to report the P value, which tells the significance. These are three separate things that each give you a bite of the data. Then there's multiple regression. Okay, so I've got a bunch of factors. We've got the sunny days. We've also got the amount of watering that I do. We also have any fertilizer I may use. It just so happens that the soil richness is a dynamic variable as well. I don't know if you may or may not have seen, there was grass all over there, dead grass. So I mulched the soil. I also shoveled cow poop into some of that soil, having access to manure. And I shovel compost into the soil. So the soil richness does vary. So if we have sunlight, watering, and we have the amount of fertilizer, the amount of how good the soil is, this will all go down to how thick our carrots are or how much squash we produce. But there are all these different factors. Which factor is the most important? Well, we need multiple regression for that. And that is a much more statistically complex test that will test the strength of each factor on the variable, and will compare the factors to one another to find out what is the strongest correlation and what are the weakest correlations. There may actually be correlations between factors. I don't water my plants on days that it rains. It just so happens that most days when it rains have less sunlight. So there is a there's a positive correlation between sunlight and watering. There's also a negative correlation between how well water works in the sunlight. On very hot, dry days, that little watering can that I added in the morning won't last past 11 a.m. So the hotter and drier sunny days are actually going to decrease the amount of water efficiency. So this kind of correlations, the quadratic correlations, many factors, each of which can have their own quadratic or linear kind of impacts on the output. It's complicated. It's beautiful, though, especially if you know what you're looking for. Anyway, what are you looking for now? Stats. I want you to go online. I want you to find a scientific paper. I want you to look at the end of the introduction, and that's where we are probably going to find the hypotheses. And then I want you to go to the results and just list the statistical tests used. You don't even have to read the results. You can just read the figures, and the figures will tell you what stats were used. I mean, in a well-written paper. Like yours, right? So read the hypothesis, list the statistical tests that are used, and how, are these tests we covered, or are they doing something like a random forest test, or maybe a MANOVA? Maybe they're doing something you've never met before. It might just be worth it, just Wikipedia that thing and see what you can learn. So there are a lot of statistical tests that we did not cover. In these few stats lectures, we've covered mean, median, mode, and a little bit on bar graphs, error bars, and then some very simple tools like t-test, ANOVA, linear regression, just some really simple tools for your tool belt. There are a lot of other things out there that can be used. So a wide world of statistics awaits. Go enjoy some, review some, and always feel free to ask me questions about statistics. I am still learning as well, and I always like meeting a new confusing mathematical test.